Hey everybody, and welcome back to Algebra 2 Online. So today we're going to talk about a very cool thing because we're going to talk about a new kind of number that you don't know about, and I think that's cool. So to motivate this, I want to actually just solve a quadratic. So this one right here you can't easily solve with factoring, so we're just going to do the quadratic formula. X equals negative b plus or minus square root of b squared minus 4ac all over 2a, which is just 1. And if we simplify this, 4 minus 8 in there, right, is negative 4. And this is something that maybe your Algebra 1 teacher said, like, is just undefined, or maybe hopefully they said something along the lines of just wait on that, because we'll talk about that in Algebra 2. And that's what we're going to talk about right now. So this is a different kind of number than you know. And I'm actually going to come back and I'll write out what the answer to this problem should look like. But if you graph this quadratic right here, it looks like this. And you'll notice the x-axis down here, it's like floating above the x-axis. So in Algebra 2 or Algebra 1, you might have just kind of said this didn't really have a solution or something like that. But here, like, we're never going to say a quadratic doesn't have a solution. That's wrong. They always have solutions. They just might have these weird solutions like this, and this being negative under the square root means it's really a different kind of number. So it's like still crossing, and it has a root. It still crosses like an axis, but it's crossing it somewhere that you can't really see. So yeah, that's what we're going to talk about today. So this is like a very important diagram that hopefully you saw something like this in like Algebra 1. Actually, I was just talking to an Algebra 1 teacher, and I know that he is showing it. So hopefully you've seen something like this. But, you know, these are just different number sets. They have different names, just to kind of like put a few down. So the big bubble in here, this is what we call like so I'm going to outline it as best I can, which actually turned out better than I thought. So that purple big bubble is what we call the real numbers. We've been using that symbol a bunch. The real numbers are broken down the middle right here by rational numbers and irrational numbers. Rational numbers are just your ones that can be written like a fraction, like 1/2, 1 over 2, 2, 2, because why not? Negative 7 is a fraction, right? It's just over 1. Actually, negative 7 over 1 is in a different set of numbers that's in there, so let me change this to negative 11. Negative 7 is actually an integer, and so all your integers are rational numbers. They all can be written as a fraction, but they are all over like 1. Integers are just your, negative numbers. They also include 0. 0 is actually what we call a whole number. But it includes also things like 2, which is like a counting number, and the counting numbers are the natural numbers. You count like 1, 2, 3, 4, 5. That's your natural numbers. So these are just a few examples of kind of the nice ones. The not so nice ones are like irrational numbers. These are things like square root of 2, pi. You're going to learn about something this year called e. There's something called tau. There's something called phi. There's so many here, like square root of 3. Anything that doesn't have a fraction is in this bubble. And this is kind of misleading because there's actually more things in this chunk than there are in this chunk. There's different levels to infinity, and there's actually more of these. They're both infinite. This group is infinite, and this group's infinite. But there's more things here than here, which is kind of weird. So that's a really quick rundown, and all those are really important. If you don't know what some of these number sets are, I really urge you to make sure you go look up some other stuff online, but it's really like an Algebra 1 or even earlier kind of thing. So this is what you should know about numbers. But this is wrong. Well, it's not wrong. It's not fully correct. So there's actually another chunk of numbers out here. So the world of numbers has things that are not rational and irrational and all that. And that's what we call the complex numbers. And we use this fancy C. And I'll just write it here, complex numbers. So actually -7, for example, is a complex number. But there's some things out here that don't fit into any of these sets. One of them is I. That's a really basic one. You can see it over there on the left. You can have pi times I. That's another one that's not in the purple bubble. Anything with an I. So you can have 2i plus 7 is actually a complex number. And it is another one that wouldn't be inside the purple set. So the number sets really are split up into real numbers and complex numbers. There is also something called transcendental numbers, and there's some other weird things out there, but we don't really need to talk about those in this class. And I have this line right here. So I is short for imaginary, and it sounds like the numbers are fake. They are not fake numbers. The reason they call them imaginary is really just because they are the counterpart to real numbers. It's just bad naming. Really, I think the real numbers were what were named badly. And then if these hadn't been named real, these wouldn't have been called imaginary. So they're really just like the opposite of the purple bubble here. So they're the things that kind of are opposite or outside of the purple bubble. So they're just the counterpart to real. Just like you have rational and irrational, the kind of opposite word of real is imaginary. So they just called them imaginary. Just like this blue chunk is opposite this green chunk. So the simplest imaginary number is actually the square root of -1. And that might seem kind of weird, but that is a thing that you can do. And instead of writing square root of -1, we just write I. It just is the square root of -1. So if you ever get this in a math problem, you'll just write I, okay? Actually, I can go back now. I'm going to talk about these in a second, but let's just go back here now. So if I was to write the answer to this, so we know that like when we simplify roots, right, we have this rule where we can, if the product of them, the product of these two is the square root of -4 in there, we multiply these. It's like a thing you learn in Algebra 1. So we can do that. And then we can simplify things now a little more because the square root of 4 is 2, but that we just said that the square root of -1 is I. So we're going to put an I there. And then you could divide everything by 2 also. So actually, this is the answer to this quadratic. There are 2 roots to this quadratic. They are complex numbers. They are just, again, complex numbers is just something that's not a real number. We'll talk about like why we actually write the answer this way in a second. But basically we can't combine these anymore. They're too different. They're not like terms. So that's actually the answer to this quadratic. But let's go back here. So something kind of interesting happens if you do powers of I, okay? So if you do I squared, you would just take the square root of -1 and square it, which is -1. And this is actually like what a lot of people view as the definition of an imaginary number. So they are numbers that when you square them, you get a negative. Think about that for a second. Normally, when you square a number, you get positives. But these are numbers that you square and get a negative. They totally exist in the world. Actually, we realized a long time ago that our math was not working well, and we were like, why is this happening? And it was because we thought the world of numbers just ended in this purple bubble right here. But we realized we were very wrong. In order to solve a lot of problems, you had to have this stuff out here that fits this idea, where if you square it, it's negative. So students always love to say, well, if you square a number, it's positive, but that's not true. If you square numbers, sometimes they're positive, but sometimes, like this, they're negative. And that's actually a very important result, and it lets you solve a lot of real-world problems, actually. So I want to keep going with this. So if you do I cubed, that would be I squared times I. And we just said I squared was -1, right? This I squared is right there. So then this is negative I, right? The negative being the -1. That looks kind of confusing. So actually, if we ever run into an I cubed, we never write I cubed. We just write -I because it's the simpler version. It means the same thing, right? If I keep going with that idea, I to the fourth is I cubed, that's a cube, I cubed times I. And we just said I cubed is -I. So then if I put in a -I times another I would get -I squared. But we also just saw up here that I squared was -1. So we can simplify that even more, and we can say that's really the negative of -1, or just 1. So if we ever run into I to the fourth, that's actually really nice, because I to the fourth is back to a real number, like one of the ones that you're used to. It's just 1. If you just raise an imaginary number to the fourth power, like this specific imaginary number, you get 1. And this ends up being really important, because if you think about what's going to happen, at this point, if you jump to I to the fifth, right, which is I to the fourth times another I, then it's like saying, what card do I want to use? So 1 is I to the fourth. So I'm going to plug in, I guess I'll write it here, a 1. And then I have multiplied by an I, which is just I. So I to the fifth is back to I. It's just back here. If I go one more time, I to the sixth, I to the fifth times an I. Well, we just said I to the fifth was I. So we're just going to swap that out. And then I times I is I squared. But we also just said I squared up above was -1, right? I squared, -1. I to the fifth is I right there. So you should see that there's it's impossible to actually get certain powers of I. We never actually write anything besides I to the first power. We never do. I only did this to teach it. So we do I, that's the square root of -1, we just write I. I squared, we just write -1. I cubed, we just write -I. I to the fourth is back to 1, so then everything restarts. So I to the fifth is I to the sixth is really an I squared, but that's -1. So the only ones you'll ever write, you write I, you write -1, you write -I, and where is it? And you write 1. Those are the only, for the powers of I, those are the only numbers you'll ever write. And this really is a number. So it's kind of weird, but it does actually make a lot of things a lot easier. For example, this. So if I had I to the 30,494, that is not something we would ever write in math, because there's a much easier way to write it. It's either going to be an I, it's going to be a -1, a -I, or a 1. So because it's a cycle of 4, what you can do is you can take that crazy exponent, you can divide it by 4, and you can basically look at the remainder. So if you do that out, you get 7,623.5. But this is the important part. So this little, I'm going to draw a little table. This is a very important table to make note of. So if you ever run into these big exponents, you can simplify it really quick just doing a division by 4 because of the cycle of 4. So there's only 4 numbers. Again, you can have an I, you can have a -1, a negative I, or a 1. And basically, if it's like an I to the 4th, which was our 1, then the 4 should divide in perfectly and leave you with no remainder. So this would be the case if there's no remainder. If it's the first one in the cycle of 4, you're going to get a remainder of 0.25. If it's the second one in the cycle of 4, which is the one we have, you're going to get a remainder of 0.5. If it's the third one in the cycle of 4, you're going to get a remainder of 0.75. And then, of course, this case, you just wouldn't get a remainder because it's a multiple of 4. If you do like I to the 8th, you do 8 divided by 4, right? You get no remainder. And that's because this is like I to the 4th times I to the 4th, which is like 1 times 1, which is 1. So this is a very useful sort of table to know, and it comes purely out of what I was doing here, where it's just this cycle of 4 that you run into. So formally, I just wanted to define a complex number. So a complex number is one that has a real and imaginary part, okay? And real and imaginary parts are two different kind of things. If I asked you to simplify this expression right here, all you could do is say 3x, you could combine the x's, right? And then you have minus 3y. But you can't do anything else because x and y are different kinds of things. So that's the same for these complex numbers. I and 5, they're both numbers, but they aren't like terms, so you can't combine them. You can do things like I plus 5, you can say that. You can do I minus 5. That means things too, but there's no way to take these and combine them into one thing. You can do 5 times I, that's fine. That's actually purely imaginary number that is, just has an imaginary part. But these two things, this is imaginary, this is real, so that's one of these complex numbers. And just to kind of show you how we'll run into that, I could ask you to simplify something like this, and you still do normal double distribute stuff. So you're just going to double distribute everything. You would get 18 minus 6i plus 36i, and then minus 12i squared. And then that's a pi right there. So these are like terms, right? They're both imaginary numbers. So I can take 6 away from 36 and get 30. This, remember, I squared, we never write I to any power but 1. So this should be simplified. And that's the one where it's a -1. And so then really that last part is plus 12. And then you can do now this and this are real numbers. So you can do 30 and then write plus 30i. But this is as far as you could go. You can't combine those anymore because it's one of these complex numbers, just like this idea, where they're not like terms. You're not going to be able to say 60i or something like that. I want to do just a few more kind of quick here. We kind of did the first one actually because of that quadratic in the beginning, but if you ever have square root of a negative number, that's what you're going to see. And a lot in this course, and then you're going to have to know to simplify it with imaginary number. We can write this as square root of 64 times square root of -1, and so that is 8, and then times I, right? This and this is the I part, and then square root of 64 is 8, and that's it. That's how we write this number. We would never write this. We would always just write this. They are the exact same thing in math. You might get weird expressions like this. I think this one actually is a SAT problem. I pulled it from somewhere. But a lot of this stuff works the same way. You like distribute here, right? So I'm going to get minus 3 plus 5i. And then I might as well do this too. So square root of negative 1 is I. So I'm just going to write plus I at the end. Then just combine like terms. So 5 minus 3 is 2. 3i plus 5i plus another one is 9i. So that's what that one would become. And then this is one of these kind of classic common mistakes problems. So if you ever square a binomial, which is what that is, right? We have to multiply it by itself. A lot of students don't want to do that. They just want to put this power of 2 on these two things, but that's not what it means. You need to multiply this thing by itself. And then it's just like one of the other problems we kind of did in the previous slide. Like multiply this through, you get 9 minus 12i minus another 12i, and then plus 16i squared. So the middle 12s become a 24i now. And same thing, this is a negative 1, so it's really like minus 16. And then 9 minus 16 is negative 7. So negative 7 minus 24i. So that is as simple as you could go for that last one. I thought I would just do one more quadratic here. So, this is a problem where one thing that I would maybe do first is multiply by negative 1, just because I don't like the a term to be negative. So then I get 2x squared minus 10x plus 15. And a lot of times, when this is a prime number, you might be able to try to factor it. So I would try. So I would do like, it has to be 2x, and then it has to be x. You have to multiply to 15. So you can think of just like trying some different things in here. You could do like 5 and 3 or something. You could try, and multiply out this then, and you would see that like if you do this and this, you get 10x plus 3x, which is not negative 10. You could try it as many times as you want, but this is a problem that is not going to be factorable because I made it a imaginary number one. So let me get this kind of out of here. So I would just, after you try to factor it, I would just do quadratic formula. Negative b is 10 plus or minus square root of b squared minus 4 times a times c, and then all over 2a, which is 4. And then if you multiply out the inside there, you have 4 times 2 times 15, which is 120. So you got 100 minus 120, all over 4. And so this part in here is the square root of negative 20. And as soon as you get to negative under a square root, now you see that you have one of these imaginary numbers. And I personally would write the answer this way. So I would do 10 plus or minus the square root of 20 and then just stick an I right there. That's how I would want the answer. If this was a perfect square, I would want you to take the square root and see if it simplifies more. But it's not gonna be nice. I mean, you could do square root of 4, square root of 5, and you get a 2, and you could do a little bit more. Let me just write what I'm talking about. So you could do this. And then you could do the square root of 4 is 2. So then you could take a 2 out of, top and bottom. And you would get this, this answer. But honestly, I'd be fine with this solution also. The big thing is that you honestly see that there's a negative, and so you see that you have to take, you have to write an I there. I'd be fine with this one too. This is like how you'll probably see it in like a lot of, things online and textbooks and different things like that. That would be like the most reduced answer, but I am fine with this one also. The big thing is I don't want this answer. I want to make sure that you know that this negative in here is translated into an I right here.